So in this slide, we are on slide number 12 now. I show you that there are two-tailed tests, and this is associated with this type of alternate hypothesis, the not equal to. So we're not claiming that the alternate hypothesis is on one side or the other. We're just doubting that mu is equal to 23. And then we can have a left-tailed or a right-tailed test. Mu is less than 23 or mu is greater than 23. So down here, I've got three diagrams of the normal distribution, and I'm showing you that when we have a two-tailed test, then we calculate the area in both extremes. And again, the suspicion gets greater when we get further away from the center. Here we're not very suspicious, still not that suspicious, but as we get more and more over here, we start to get more and more suspicious until we reach the threshold of suspiciousness, and then we reject the null hypothesis at that point. I'm going to erase that so you can see those diagrams a little better. So yeah, the shaded blue area is where we would reject the null hypothesis. And it's really based on area, because area is probability. When we have a two-tailed test, then alpha is split between the two tails. But when we have a one-tailed test, then alpha is just over on one or the other sides of the distribution. And we can still use normal CDF to find that area and decide whether we're at the threshold of suspicion or not. Before we get into how to do hypothesis testing, we need to have a couple of ground rules to keep us safe. When you perform a hypothesis test of a single population mean mu, using a normal distribution, your sample size must be sufficiently large, or you must know the value of the population standard deviation. So this is unlikely. So the alternate is to have a sufficiently large sample size, and generally n equals 30 is our rule of thumb. Although I've heard real people say that might not be true in different applications, but for this textbook, we'll just stick with the rule of thumb that n has to be bigger than 30. For the t-test, your data should be a simple random sample from a population that is approximately normally distributed. And you use S to approximate sigma. And again, I consider this almost like the legal fine print. If we don't take care of this, then we could get in trouble and make conclusions that are not valid. And finally, for the test of a population proportion, the shape of the binomial distribution needs to be similar to the normal distribution, so check to make sure that n times p is greater than or equal to 10 and n times q is greater than or equal to 10. Then we can just use the normal distribution. Mu will be the same as p, and sigma is equal to the square root of pq over n. So I feel like right now I'm nervous that I'm going to forget about this, and this is the kind of thing that you just put on your notes sheet to double check this. I mean, I'm not intentionally going to try to trick you and give you one where these conditions fail, but if these conditions fail, then we can't make conclusions. If the conditions fail, then maybe we just have no conclusion. No conclusion. Okay, so we want to assume that the null hypothesis is true, right? That's kind of our default position. I kind of think about it as like anytime a student comes to tell me something, I always default to believing their story. But then at some point, there's going to be enough evidence where you're like, nope, I have to reject that hypothesis. So when we assume that the null hypothesis is true, what is the probability that we get a certain sample mean or worse? So here's what I mean by this. If mu is 50 and we end up with a sample mean of 54, you might be like, that's a little bit suspicious. We find the probability that x bar is greater than or equal to 54, and we learned how to do that by doing second distribution, normal CDF, 54, 1, E, 99, mu is 50, and the standard deviation, I'm going to tell you in a future slide, is 4, divided by the sample size. So what is the likelihood of getting a sample mean that is 54 or higher? And this is a perfect opportunity for me to talk to you about tiny numbers, because you might be like, that's not a probability. That's 7.87. That is actually this number right here. So I'm going to show you that 7.8, let's just call that 7.83, E negative 4 really means 7.83 times 10 to the negative 4th power, which means take this decimal and scoot it to the left 1, 2, 3, 4 times. 1, 2, 3, 4 times. Put your decimal there, fill in with zeros, and that's how we got this number. If you round, you get 0.0008. That is the probability that we would get a sample mean that is 54 or higher. So that is a very suspicious area P. Low P means high suspicion. Or we could assume that mu is 50 and we got a sample mean of 51. That's not that suspicious. So the area P value, and the reason I'm calling it an area P is because there's too many P's in this class already, and now we're dropping a new P, so I just call it the area P. The area P is the probability of getting the test result or weirder. And what I mean by or weirder is, what is the probability of getting 54 or greater? What is the probability of getting this? So that is the area P. Probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained. A small p-value indicates we should reject H0. Alpha is the preset level of significance for the test. And often we'll have an alpha of 0.05. That's a pretty popular one. Just like last time we had the confidence level of 0.95 was a very popular one, although we sometimes had a confidence level of 0.90, and that would be associated with an alpha of 0.10. So the area P is the area in the tails for the given statistic. And we end up comparing the area P with alpha. And that's how we decide when P is greater than alpha, we fail to reject the null hypothesis. There is not enough evidence to reject the null, and we're a little bit bummed. The more exciting alternative is when P is smaller than alpha. Remember, a low P area indicates a high level of suspicion. So the tinier P is, the more suspicious we are, and we reject the null hypothesis. There is enough evidence to reject the null, and it's more exciting and dramatic. So this is all the things in the middle are kind of what we would expect to see if the null hypothesis is true. And then we have this threshold, the statistical significance threshold. This picture is for a one-tailed test, it looks like, because we only have shading over here. And we get an observed test result. So this could be our sample mean or our sample proportion, this green dot. And so the area to the right of it becomes our area P. And again, we're pretty far from what we would have expected if the null hypothesis is true, so we're getting a little bit suspicious. And we're going to get that area P and then compare it to alpha. So should we believe the null hypothesis? A normal distribution has a population standard deviation of 4. This is actually going back to that example of a whole bunch of little kids, and the population mean was mu equals 50. We have sigma is equal to 4. Our sample sizes are 10. And then we do a sample, and we get x bar is equal to 51. So our null hypothesis is that mu is 50, and then if there's enough evidence, we can reject it and go to the alternate hypothesis that mu is greater than 50. I'm going to tell you right now, this is not that suspicious, but you can't just look at it and decide that. You have to do the math. So we're going to go through the process of drawing a graph that shows the p-value. So it will look something like this, but I'm going to clear this out and show you stat tests. We're going to do a z-test. So stat tests z-test. I'm going to input the stats, not the data, enter. Then I go down to mu 0 is 50, sigma is 4, my x bar was 51, sample size is 10. I think I already, that's not a very big sample size, but because the data is from a normal distribution, I might be able to get away with that. And then my direction is what I need to pick next. So I'm going to pick this direction, enter, because the alternate hypothesis is mu greater than mu 0. And I don't care about the color, blue seems great. And then I'd like it to draw a picture for me. And I have some other stuff going on my graph, which I think those are the graphs from the potato weights. I'm going to go turn those off. Let me show you. Second, stat plot. I need to turn all of these off. So I'll just hit 4 for plots off, enter. And then when I press graph, darn it, I think I have to do this again. So stat tests z-test, and I'll go down, everything should still be there, and then click draw. Okay, so there is my picture for this situation, and I have mu is equal mu 0 is equal to 50 right in the middle, and I wasn't that far off. My x bar value was 51. So see how this shaded area is pretty big? The area P is equal to 0.2146. So that's a pretty big shaded area. I'm not that suspicious about my null hypothesis. And if I quit out of here, you can see that a second ago, I had just done a normal CDF process, second distribution, normal CDF. This time I'll do 51 to 1e99, mu is 50, and sigma is 4 divided by the square root of 10. If I do this, I will get that area P, and I must have screwed something up. Oh, that's 51. Second distribution, normal CDF, 51 to 1e99, mu is 50, and sigma is 4 divided by the square root of 10. That should be correct. Enter. Okay, I had a typo in the previous round. So now I'm getting the same area p-value of 0.2146, so I feel good about that. Not too suspicious. And then what if we had the exact same story, but now the sample mean is 54? So same story, mu is 50, but now I'm getting an x bar of 54. So it's going to be further over. Let's go through that process again, and I'll show you how we get this area P of 0.0008. Stat tests, z-test, mu is 50, sigma is 4, and I don't have to put in 4 over root 10. This test asks me for the sample size, so all I have to put in is the x bar, and then everything else stays the same, and I'm going to have it draw the picture again for me. And notice that this time, there's your 8e negative 4 for the area P. I'm going to erase the way I sketched this because 54 is actually off the charts. It's like way over here. I can't even see anything on the graph there. So there's no visible area, or we could just say it's super tiny. There's a tiny, tiny shaded area right here, and it's just not visible. So the area P, again, it's 8e negative 4, or 8 times 10 to the negative 4, which means 8 times 0.0001, which means 0.008. So super tiny probability of getting a sample mean that is that far away from the population mean. So I think I've gotten a pretty good explanation of how the hypothesis testing process works. We have a preset value of alpha called the significance level. If p is smaller than alpha, we're really suspicious and we reject H0. There's enough evidence to support the alternate hypothesis. And then if p is greater than alpha, we fail to reject the null hypothesis. And then again, here's the convoluted explanation. When we don't reject, it doesn't mean that you should believe H0 is true, just that the sample data failed to provide enough evidence to cast doubt on H0. So it's convoluted. I know that's kind of an annoying explanation. So then we will write our conclusion at the end of the process. And I think we're almost done here. Level of significance is alpha. You should select the alpha first before you start getting the sample data. And then alpha equals 0.05 is a default that you can use if nobody says anything about that value. Just default to that one. The p-value is the area in the left tail, right tail, or split between tails. And a couple more slides here. Different types of errors. Type 1 and type 2 error. I kind of like using this wording here. A type 1 error is that you were too suspicious, and a type 2 error was that you were not sufficiently suspicious. So in the type 1 error, the null hypothesis was true, but you rejected it. The type 2 error is H0 was false, but you failed to reject it. The probability of a type 1 error is alpha, and the probability of a type 2 error is beta. I kind of just tuck this away as useful information, but I won't be asking you too much about this. I do like you to have a little note about this on your note sheet in case I ask you about the difference between the two errors. But I think about, like, again, believing a student. A type 1 error would be that the student was telling the truth, and I thought that they were lying. Type 2 error would be that the student was lying and I believed them. So those are both errors. And then this is just a nice graphic that shows you if the null hypothesis is true and we fail to reject it, then that's good. If the null hypothesis is false and we reject it, then that's good. So I'm looking at this and saying, yes, we want to be either here or here. But what if the null hypothesis was true and I rejected it? Then I was too suspicious. Or what if the null hypothesis is false and I failed to reject it? Then I made a type 2 error. So I know this is a little mind-bending, and honestly, I can't really hold this in my brain at the same time as I do all of the other analysis we're going to be doing. So I just try to remember this, sort of keep it on your notes sheet. It's honestly easy for me to get mixed up between type 1 and type 2 unless I look at my notes. But I think you can understand that there are two different ways that you could go wrong in this process. And finally, this is just a reminder that if we have an alternate hypothesis that looks like this, we have a left-tailed test. This would be a right-tailed test, and this would be a two-tailed test.